Hello, everyone, and welcome to our presentation titled Advertising Fraud Detection at Scale at T-Mobile. My name is Eric, and I'm a data scientist, and I'm joined by Fawn, who is a data engineer. Both of us are on T-Mobile's marketing solutions team, which is a new team within T-Mobile that provides services to the advertising industry. We'll be talking today about a research project we developed intended to identify potentially fraudulent ad activity using data gathered from T-Mobile's network. We'll be discussing some of the challenges we faced and other tips we learned in the process of developing this tool. To give you an overview of the presentation, we will start with some background information about the ad tech industry. Then Fawn will talk about Spark tuning and optimization. Then we'll discuss Spark code for those with Python background and some specifics about one of the algorithms we are using to define fraud. And finally, Fawn will finish by explaining our process of automating the project and our use of MLflow. Again, before we get into the details of the project, I want to give some background about the ad tech industry for those less familiar, because it will help explain why ad fraud is such a difficult and pervasive issue. To give you an idea of the scale, it is estimated that advertising fraud costs advertisers about $23 billion in 2019, and that number is expected to grow in the coming years. You could say there are two main reasons why ad fraud is so prevalent. First reason is a general lack of regulation around online advertising, although that changed a bit after CCPA started being enforced earlier this year. But federal and global regulations are still fairly lax. The second reason is that the ad tech industry is fairly complex and not well understood by most people. With so many moving parts, it can be extremely difficult to monitor everything that goes on during an ad transaction, especially when the average American is exposed to about 5,000 ads every day. To give you an example of the complexity of ad tech, here's a diagram of the main components used during an online ad campaign. You're likely familiar with the idea of an advertiser and a publisher, but there are a few more components that control the movement of information and determine who sees what ad and when. For each impression, this entire process of determining which ad to show, how much the ad will cost, and who will see it takes less than a second. And each moving part presents an opportunity for fraudulent activity to occur. Although since it is almost always the advertiser who is the one losing the most money, the fraudulent activity is most likely to occur on the side of the publisher. This is made more apparent when we dig into the two main types of fraud. The first is a bot farm. A bot farm is essentially a collection of devices with the sole purpose of browsing a particular website or app, or to generate ad impressions for that publisher, while the publisher benefiting from the ad impressions and the clicks. But to be clear, everyone except the advertiser makes money in this scenario. The other main type of fraud is referred to as domain spoofing. This can take several forms, but simply it is the process of a publisher sending a URL to the SSP that is not the actual URL of the publisher to trick everyone upstream into thinking they are sending the ad to a legitimate website. And this leads us to the question of how we identify fraudulent activity. The first thing we need is data. We need to be able to see and track what is going on in the billions of online ad transactions that come through our network. Being a telecom company, we have the advantage of being able to utilize all of the network data used by T-Mobile devices. Second, we need to use this data to develop a model that can identify several different types of fraud. And lastly, we need to be able to scale this model to handle the 4 to 10 terabytes of data that T-Mobile collects every day. There are a number of technologies that we use at T-Mobile, including both on-prem and cloud-based platforms, as you can see here. There are instances where we use a hybrid approach. But the most important thing is to develop a working pipeline that can extract data from its source so that the data can be used to train a model and generate the required outputs. The process always carries data from its original format, whether that be ORC, Parquet, or CSV, to the desired output, whether that be a table of metrics or a dashboard for visualizing data. Many data scientists like myself are used to working with Python and SQL to accomplish some or all of these tasks. But when the scale of data becomes great enough, for example, when you're dealing with terabytes worth of data, Spark becomes a necessary tool. Hive and SQL don't really have the machine learning tools required to do most data science work, and Python just can't handle such large amounts of data. So with that in mind, I'm going to pass it over to Fan, who is going to go into some more detail about Spark tuning.
Hey everyone, my name is Fan. I'm a data engineer of data scientist team at T-Mobile Marketing Solution Group. Working with Spark daily means you are going to involve a lot with resource allocations, as well as reading, writing, joining, and aggregations, which just happen to be our topics today. When you start your Spark applications, this means it's static allocation by default. That means you have to tell resource manager exactly how many executors you want to work with. The problem is you usually don't know how many executors you actually need before you're doing your job. Isn't that obvious? You often allocate too few that make your job very slow and even fail, or you allocate too many that you're wasting a lot of resources. In addition, those resources are going to be occupied by the entire lifetime of your application, which also leading to waste resources unnecessarily. That's why the flexible mode called dynamic allocation come into place. With this mode, executors are spinning up and down depends on what you're working with, as you can see in the left chart here. This mode, however, comes with a bit of setup. You may want to set the initial and minimum executors. As the name suggests, those are the minimum resources for your app. Take a bit longer to spin up, but it's faster when you're executing your jobs. You may also want to set the maximum executors because without any limitation, your app can take the whole cluster, take over it. Yeah, I'm talking about 100% of the cluster. Executor either timeout config will keep your executor leaves a bit longer than it should while waiting for a new job. Otherwise, it would be killed by idling, and a new job will require new executors, which need some time to start, which also cause some delay. Cache executor either timeout config will release executors, thus saving your cache. Mind you, if you don't set this up and you cache the data quite a bit often, this dynamic allocation would not become much better than static allocation. Spark doesn't read files individually, it reads in batch. You try to merge files together until a partition is filled up. Think about this odd use case. You have 1 million files in a HDFS directory, and you have 1 gigabyte of data with 1 million files. So you have 1 byte per file. With the configuration max partition by 8 megabytes here, you will have about 500,000 tasks, and the most likely job would fail. The bottom left chart shows you the correlation between number of tasks and the partition size. It's simple. The bigger partition you config, the less tasks you will have. Too many tasks will make the job fail because of driver memory error, AM memory error, or network connection error. Too less tasks normally would slow down the job because of lacking parallelization. And often it would throw executor memory error as well. Fortunately, we found a formula that can calculate the ideal partition size. It involves data size, number of files, number of directories, number of executors, number of cores. Apply all of those parameters into this formula. From the above example, you will have partition size about 2 gigs and 2,000 tasks, a much more reasonable number. When you join a table or do any aggregations, Spark will shuffle data. Shuffling it's a very expensive job. Your entire data set will be moved through network connections between executors. Tuning this shuffle behavior, however, is an art. Take a look at this thought example. A mismatch between shuffle partition config, I have 4 here, and the number of current available threads, 8 in this case because I have 2 cores for executors, we get 4 threads for nothing. The ideal shuffle partition can be calculated by this formula. You can get it you can easily get the number of executors if you're on static allocation mode. But how about dynamic allocation? Use max executor if you have it, or if you don't, I'm telling you a secret. try to use the number of subdirectories of the folder you're reading from. Writing in Spark, it's a bit interesting. See the lab example here. If you have 1,000 executors, you have 1,000 files. The point is, we couldn't know if that is too many files or too few files until we know the data size. From our experience with huge data, keeping file size less than 1 gig or keeping file size less than 1 gig and the number of files less than 2,000 is good enough. In order to do that, you can do either coalesce or repartition. Coalesce, it's good enough in general if you want to scale down the files. Repartition, on the other hand, with shuffling stage, will speed up the job if your data is skewed, like the right example here. Of course, it will be more expensive. Now I'd like to show you a quick demo about how this Spark tuning and how effective it is in our case. Our demo today has 2 sections. First, we would like to show you our customized kernel and its features. We call it MySpark. This kernel is our attempt to work with Spark using Jupyter on an on-premise environment. It allows us to set up Spark configurations on each notebooks easily with a restarting Jupyter. It's extremely useful for data engineer who has to work with different scale of data and need different set of configs for each dataset. It's integrated with SQL, so instead of typing dataframe.show 20 commas false all the time, you can simply use magic cell SQL, type your query, and enter. It also applies a permanent fix for the broken format when you're displaying Spark data frame. It connects to Spark UI and gives you a quick review of current job progress. Now let us present you the optimization technique that we mentioned. We apply it into 2 datasets. They are almost exactly the same about data and structure, about 740 directories and about terabyte daily. The main difference is the first one has about 250,000 files and the second one has only 1100. If we read them both using default configs, for the first one, you have 16,000 partitions, then therefore you have 16,000 tasks when you perform an action that going through entire dataset. It took about 20 minutes to finish. For the second one, it's way less files. Number of partitions is about half compared with the first one, and it took only 5 minutes. Now let's apply the formula we showed you earlier. Is equal with data bytes plus the number of files times open cosine byte, which is 4 megabytes here, all divided by number of executors, which is number of directories in dynamic allocation, time number of cores from our configuration. We're gonna print out some useful information so we can refer back later. Then we run the same code as before. You can see the number of partitions drop to less than 1,000, and where the execution time is reduced to half. What if we apply the fix for the second dataset? We ended up with 800 of partitions and tasks, and less than 2 minutes to accomplish the job. Now, Eric, our data scientist talk, will go through another aspect, how a data scientist would work with PySpark.
Many data scientists code in Python. This is the programming language I am most familiar with, and I know there are many other data scientists with similar backgrounds. Making the transition from Python to PySpark can be challenging for anyone, so I'm going to talk through an example of some code I needed to write in PySpark and how I got there with the help of a UDF. For a lot of what data scientists might do on a day-to-day basis, there are many similar functions and methods in Spark that would be familiar to someone used to working with the pandas and scikit-learn libraries. For example, reading a CSV file, splitting your data into chain and test sets, and fitting a model are all things that have similar syntax between the two. And if you are using only predefined methods and classes, writing code in Spark may not be very difficult. But there are a number of instances where converting your Python knowledge into Spark code is not straightforward. Whether that be because the code for a particular machine learning algorithm isn't in Spark yet, or the code you need is very specific to the problem you are trying to solve, sometimes you need to write your own code in Spark. And with Spark's cryptic error messages to guide you, that may seem like a daunting task. So I'm going to show you a piece of code that I wrote for this ad fraud project, first as a UDF, and then as Spark code, and then talk through how I got there. As someone who is more comfortable writing in Python than Spark, I decided to first write out my code as a Python UDF, which you can see here. Once I did that, I broke my code down into logical snippets, or lines of code that performed a fairly basic task, which you can see outlined in the colored boxes. From there, I was able to find a function, or more likely a group of functions, that served to accomplish the task I set out to complete. After doing this for each of the logical snippets, I just had to make sure that the bits of code fit into each other and test that the end result was more or less the same. Then I was left with code that ran in Spark rather than a Python UDF. And to justify this effort, here are the results showing the difference in performance between the UDF and the PySpark code. PySpark code ran over twice as fast, which for a piece of code like this that runs every day is saving many hours of compute time over the course of the year. So now I want to take a minute to talk briefly about one of the metrics we use to identify potentially fraudulent activity in our network. The metric is called normalized entropy. For the data scientists watching familiar with decision trees, you may have used or know of Shannon entropy, which is a metric commonly used to calculate information gain. Normalized entropy, in this case, is the normalized form of Shannon entropy. For those unfamiliar with Shannon entropy, it is defined by the equation in the top right as the negative sum of p of x times the log of p of x for all x, where x in this case is a T-Mobile customer, and p of x is the number of times a given app shows up in customer x's network, or c of xi, divided by the number of times the app shows up in the entire network, or c of capital X. We get the normalized entropy by dividing Shannon entropy by the maximum entropy for a particular app. And the equation for this is given just below the other one. It is defined as 1 minus the sum of c of xi times the log of c of xi divided by c of capital X times the log of c of capital X. You can then multiply by 100 to get a value between 0 and 100. The idea behind this metric is fairly simple. Since common apps tend to get intermediate traffic from a number of different people, we would expect safe apps to have a value of around 40 or so, give or take a couple standard deviations. You can see this by the histogram in the bottom right corner, which shows the distribution of normalized entropy values for all the apps we are tracking. Whereas values that are close to 0 or close to 100, we would score higher in terms of their potential fraudulence. This is, of course, not a flawless metric, which is why we include several others in the final analysis. For example, often people only use their banking apps every few days, so apps like these would have a higher normalized entropy, but are unlikely to be fraudulent. Now, back to Spark. The code you see in the top left is a code we are currently using to calculate normalized entropy. And what you see on the right is the time difference between running this code with the default configuration and an optimized configuration. The optimized config sets the executors to 100, 4 cores per executor, 2 gigs of memory, and shuffle partitions equal to the executors times cores, or in this case, 400. As you can see, the difference in compute time is significant, showing that even fairly simple code can benefit greatly from an optimized configuration and end up saving you a lot of waiting time. This is a great skill for all data scientists to have who are analyzing large amounts of data in Spark. The last thing I wanted to bring up with regards to Spark configurations is the difference between static and dynamic allocation. The two previous configs were static, but when I used dynamic allocation with the dynamic equivalent of the static config shown in the top right, the dynamic config takes almost twice as long to compute the same data using the same code as the static config. The reason for that is that the Spark cluster will initially only spin up the minimum number of executors. It is only when you start running your code that the number of executors increases and only is needed. This adds time, since executors do not spin up immediately and can extend your compute time. This is most relevant when running shorter jobs and when executing jobs in a production environment. So if you are doing something like EDA or debugging, dynamic allocation is still probably the way to go.
Now we scale our model to cover terabytes of data. We're ready for the next step, productionize it and turn it into a complete internal product. This is a quick overview of our MLflow platform, the data pipeline at the bottom of the architecture. which is what we talked about in the last few minutes, is scaled and put to our Hadoop production environment. The final of the algorithm, as well as the other measurement, as you can see, would be aggregated and transformed into an intermediate platform in the middle here, where web applications, analytic tools, and alerting system can reach out efficiently. As you can see, we also implement our own anomaly detection model, and together with MLflow, which we're gonna talk about it shortly, we have a complete workflow to automate, monitor, and operate this product. In this project, MLflow play an important role in monitoring phase because of its simplicity and its built-in functions for tracking and visualizing KPIs. With a few lines of code, as on the right, we'll be able to log hundreds of our metrics in no time. We tag them by dates for this visualization purpose. And with anomaly detection model in place, we can observe our machine learning model's output without constant monitoring. The last thing I want to talk about how was our marketing team would use the data generated from this project. We create an UI to help navigate the information provided. Navigating to the app for a project, we can search for information on an individual app. For example, we searched for an app developed by Kutek, a developer that was banned from Google Play Store in July of last year. We can see quite a bit of data collected about this app, including basic app information, network traffic patterns, and a just score generated by the ad fraud project. The marketing team will then be able to make decisions based on this information, whether they are comfortable publishing ads on this app. When we search for New York Times app, we can see all of the data associated with this app, including rating and just score. Other features of UI include distribution and information about metrics used to generate just score and just score itself, which will help marketers determine what just score they're comfortable with. An alternate search tool that allows for sorting and filtering by different metrics. A monitoring page will show a selection of KPIs and their values over time, including potential anomalies. We tagged them by date for this visualization purpose. And with our anomaly detection model in place, we can observe our machine learning model's output without constant monitoring. The last thing I want to talk about how our marketing team would use this data generated from this project. We create an UI to help navigate the information provided. As some of you might know, validation is a very difficult process when it comes to something like fraud due to lack of clear definition of fraud. And it's very important from legal and moral perspective to make sure it is done correctly. We are currently working with our marketing team to run A/B testing to validate our process and make improvement accordingly. And that is our presentation today. I hope you enjoy it, and we'll now start taking questions.